My dear students, I welcome all of you for today's session on system modeling and simulation. Until last sessions, okay, in last three previous sessions, okay, we had a discussion about output analysis for a single model. We had a discussion about stochastic nature of output data. We had a discussion about measures of performance and their estimation. And in today's session, we will discuss a continuation of output analysis. Okay. In this session, we will have a look at output analysis for a terminating simulations as well as non-terminating. Non-terminating also referred steady state simulations. Got it? So coming to agenda of today's session. In today's session, first we will have a look at output analysis for terminating simulation. Okay, we know, right, what actually terminating simulation means. Okay, just let me review it. Okay, and then we'll see how we can analyze the performance. Okay, how we can measure the performance for terminating simulation. Okay, and next, to measure the performance of a terminating simulation, we need to have some statistical backgrounds. Got it? We will have a look at those backgrounds. And I hope all of you are familiar with basic statistics, right? Like what I say, mean, variance, standard deviation. Clear? Suppose if you are given an array of some n elements, got it? Assume you are given a collection of some n numbers. I think you're able to compute its mean, you're able to compute its variance, you're able to compute its standard deviation. Okay, so this mean, variance, and standard deviations are some background we require to analyze, okay, the performance of terminating as well as steady state simulations. Okay, so next, after we analyze the performance of terminating simulations, we will analyze the performance of steady state simulations. Okay, at the end, we'll have a discussion about initialization bias in steady state simulation. Oh, you remember what actually bias, right? So bias means it's a difference, it's an error, right? I mean to say, when I given my model to a client stating that the performance is some X, okay? But when you run the model, okay, when you run the model, you find some deviation. You find that there's a deviation performance from what I stated, that is X, okay? It might be some 0.5 off from the X. Clear? That 0.5 I used to call a bias. Hope you remember, right? Unbiased means it is same. Bias means there's a difference. I mean, I repeat, I have developed a model and I've given to a client stating its point estimate, what we have discussed earlier session. Okay, point estimate to be some X. Got it? So when after taking a model and if he runs that model, he will find performance to be, got it, some x plus some 0.5 or 0.2. Got it? Means there's some deviation in performance what he has observed. Got it? Then compared to what I stated. So that's that we call a bias. Okay. So what we expect, we need to have a model with a lower bias, or we need to have a model which is unbiased. Got it? So we need to have point estimator which is unbiased. Got it? So how we can achieve that in the steady state simulation, we will have a look at. Clear? So now coming to output analysis for terminating simulation. So what actually terminating simulation? You know, right? Let me take an example first. Got it? So let me consider a system, say banking system. Got it? So I've developed a model. That model imitates banking system. Got it? Okay. Now I'm running the simulation for in order I'm running a model which simulates the banking system. Okay, so we know that let me say I'm simulating for a day. Got it? So bank commences at 9:30 a.m. Okay, we will treat that as time zero. Got it? Real time is 9:30 a.m. But for solving, okay, and for simulation purpose, we'll consider the start time to be zero. Then what happens? The bank will close at time 4:30 p.m. Total the bank is open for 7 hours. Got it? So closing time or starting time of a bank is 9:30 a.m. But I'll consider in simulation it as the time zero. Clear? Then bank is going to close at time of 4:30 p.m. evening. Okay, so closing time is 4:30 p.m. But 4:30 p.m. is total 7 hours. In that 7 hours, how many minutes? 7, 6, 44, 20 minutes. Okay, means I'll consider the bank is going to close at 4:30 p.m. That's the real time. But for simulation purpose, I'll consider that time as 4:20 minutes. Okay, I repeat, starting time I'm considering it as zero, and the closing time means the stopping time for the simulation. Got it? That is 420 minutes. Say for an example. Got it? So I mean, no, you got it right. I say what actually terminating simulation means that runs over a simulated time interval. Simulated time interval. Okay, it runs for a specified time interval. Say start from time zero and ends at time t. Now, what actually this t means? I said it's a stop. It's a closing time for a bank, right? I mean to say, rather than to be more precise, what I can call T means, of course, a stop time means when clock ticks to. Okay, here in simulation we will use some variable named clock. Okay, the clock initially at the start of the simulation it will be zero. Got it? And when the clock approaches, okay, I mean when clock ticks to TE, okay, an event is triggered, a stop event is triggered. Got it? A stop event is triggered at time TE. Triggering a stop event means to stop the simulation. Clear with this? Okay. Now, what actual terminating simulation? It's a simulation that runs over a simulated time interval 0 and T. Got it? So now, in this case, let me say for simpler purpose, okay, to simplify understanding, what I am taking, I am considering a banking system. Clear? For simplicity, I am considering a banking system. Okay, now I simulated for an entire day from time 0 to 420 minutes. Got it? That is in real time 9:30 a.m. to 4:30 p.m. Now, what will there are see here in this particular day, some n number of customers might have arrived to bank. Got it? So let me say n number of customers might have arrived to bank. Okay. Now, in this simulation, let me assume, okay, for simplicity, let me assume I'm considering two performance measurements. Got it? So one is the response time of a customer. Getting? I'm considering two performance measurements. One is response time of a customer. So what actually response time means? Don't get confused. I'm not telling delay of a customer. Okay. Here I'm considering what? One performance parameter is the response time. Response time means, so suppose if you have any query, okay, so you are going to ask me a query, so I need to answer, right? So what time duration I'm going to take to answer your query? That is response time. Got it? Let me tell you, for example, let me say at time 9:30, two of them have asked me a question. So at 9:30 a.m. itself, I received two questions, but immediately I can answer only one question. So means the first person to whom I am going to answer, his response time will be less. So for the second customer, or second student, what has happened? He was made to wait until I've answered for the first student, right? I mean there was a delay incurred. So as soon as the first student's question has been answered, next I am going to answer for the second student's query. Got it? So I will take some time to answer. Means here response. Here one thing you need to note down. There is a difference between delay and response time. Means for the first student there was no delay. As soon as he asked a question, I've answered him. But second student experienced some delay because he was made to wait until I've answered the first student's question. Clear? So means response time means the moment you asked your query, got it? And until the moment you receive your answer, the entire time duration I'll call response time. Got it? The moment you have raised your question, the moment you have raised your query, to the moment you will receive your answer. I repeat, the moment you have raised your query, to the moment you have received your answer. Got it? So that entire time duration I'll call a response time. Okay. So what you need to analyze here, response time may also include delay within it. Got it? Within a response time, there may be a delay. The factor delay might also be included. I mean to say, two students have asked questions to me, right? For the first student whom I answered immediately, there was no delay. Okay, response time is purely for the time consumed for answer. Whereas for the second student, he was made to wait until I have answered the first student's question. Got it? So the delay plus the time for answering the second question. Okay, I mean the delay plus the time I required to answer the second question, we call the response time for second student. Got it? So clear? I hope all of you are clear with response time and delay, right? So for simplicity here, let me assume two performance measurement. One is response time. Got it? So let me see here. Let in this slide what you are seeing, that y1, y2, yn. Okay. Let this be the response times of n customers. I mean to say, the moment they arrive to the bank, to the moment they fulfill their service and departs from the bank. Got it? I repeat, this assume this y1, y2, yn. Okay. Let there be the response time for response time of each customer. Response times of each customer. I mean, the moment they arrive to the bank to the moment they depart from the bank. Got it? So I mean, okay, and now see here what I said. This I simulated here for n customers. Okay, in this example, I'm simulating for n customers. Got it? So again I repeat, y1, y2, yn. What are they? They are the response times of each customer. I mean, the moment they arrive to the bank to the moment they depart from the bank. Got it? So I mean, as soon as they arrive, they may get serviced immediately if server is idle, right? If server is busy serving some other customer, those customer will be delayed. Clear? Got it? So now, what happened? This n, okay, this n can be a fixed or maybe a random variable. For example, what you should not get confused. How can I say the sample size n may be fixed or a random? Okay, let me tell you, there are two ways of simulating. Okay, so now in the first case, okay, I want to run the simulation. I am running the simulation, and what I need, I want to simulate here for n customers. I mean, in my mind, I fixed, okay, as soon as the nth customer arrives to the bank and departs from the bank, nth customer departs from the bank, let me terminate the simulation. Getting? See, when I say n is to be fixed, okay, when I say n is to be fixed, got it? Okay, it means I'm simulating for n customers. Got it? Means I'm starting the simulation at time 0 and ending the simulation when nth customer will depart from the bank. Getting? When I say n is fixed, I am simulating for n customers. Mean I'll start a simulation at time 0 and end the simulation at time when the nth customer departs from the bank. So yeah, n is fixed. So what when I say random variable, okay, I don't know what is n because it depends. Okay, let me say, see here, I will start a simulation at time 0. Got it? So let me say it's a banking system. Okay, bank starts at time 0, and when the bank is going to close at time 4:30 p.m. Got it? That is 4:20 minutes. I mean to say, banking system starts at 9:30 a.m. Clear? I mean simulation starts at time 0 and ends at time 4:30 p.m. Means ends at 4:20 minutes. Okay, one clock ticks to 4:20 minutes. Let me stop the simulation. Got it? Let me stop the simulation. And by that time, how many customers have arrived and departed from the bank? That is n. Got it? In this case, what I said, let me start the simulation at 4:30 p.m. and let me observe how many customers might have arrived from time 9:30 a.m. That is clock equals to 0 to time 4:30 p.m. That is clock equals to 4:20 minutes, and that is m. So this in this case, I said n is random, right? Yeah, of course. Today 50 customers might have arrived. Got it? Tomorrow 100 customers might arrive. Day after tomorrow 75 customers might arrive and depart. Got it? So n is in this case it's random. Got it? Clear? So now clear with this? Okay. Now what actually the purpose of simulation is to estimate some goal what I have decided, right? Okay, now what I said for simplicity, I said 2 performance measurement. I have not told you a second one, right? Got it? So first performance measurement, what I said, I need to determine average response time of each customer in a particular day. I repeat, I need one of the performance measurement is to determine average response time of each customer in a particular day. I mean in a particular run. Okay, in a one particular run, what may be the average response time? Got it? So what actually, how to compute average response time? I need to add response time of all n customers. Clear? Then I should divide by n. Clear with that? So what I said, y1, y2, yn, what they represents? They represent response times of individual customers. Got it? Now sum those individual response time, divide by n. That is average response time. Okay, and you should remember this average response time I used to represent using theta cap. You remember? I used to at the start of this output analysis, I told that we use theta cap. Got it? So theta cap represents average response time of one particular run. I repeat, theta cap, it represents average response time of one particular run. Got it? So now estimation of theta cap is theta. Clear? Estimation of theta cap is theta. So E of 1 by n summation I equals 1 to n yi. Got it? So what is that 1 by n summation I equals 1 to n yi? That is nothing but average response time in one run. Average response time in one run. And what is E of 1 by n summation I equals 1 to n yi? That's nothing but E of theta cap. I mean, instead of running for one time, I will perform some 100 runs, say for an example. And in all 100 runs, I will determine average response time. In all 100 runs, I will determine average response times. Clear? Then average of all average response time is nothing but estimation. Got it? Average of all average response times of all 100 runs is nothing but estimation. So got it? So the first performance measurement I am concerned is average response time. Got it? So let me say what about one more response time? Okay. Sorry, what about one more performance measurement? So one performance measurement, average response time. So in second performance measurement, okay, let it be the average queue length in an entire day. Average queue length I can see in a system. Okay, means the bank commences at 9:30 a.m. closes at 4:30 p.m. Okay, in this entire simulation, okay, entire run, what may be the average queue length that may be observed? Got it? So here, like y1, y2, yn, there is some other, okay, parameter, that is y, a function y of t. What y of t here represents means it represents the queue length. It represents the queue length of customer at time t. I repeat, y of t represents queue length of customer. Queue length of customers at time t. Got it? Clear? So now t is continuous here. Okay, t is continuous because time is continuous. Got it? Now at any particular point of t, say at any particular point of time, say t. At any particular point of time, say t. What is y of t? It gives a number of customers in the queue at time t. Got it? So at then I have run the simulation for interval 0 to t, right? Then I taught you, right, how to compute the average queue length. Got it? When t is continuous. Got it? So using integration. So 1 by te integration 0 to te y of t dt. This gives average queue length in one particular run. That I will denote as pi cap. You remember, right? In a one run, okay, the average queue length will be determined as pi cap. So what is E of pi cap? Is nothing but average of average queue length. Means instead of performing a single run, I will run the simulation 100 times. In each 100 times, I will observe average queue length. Then I will determine the average of all this average queue lengths of 100 runs. That is estimation of pi cap, and we denote it as pi. Got it? Clear with this? So hope you understood about this. Okay, so each run, what we call replications. I can you can use the replications of run one and the same. Okay, you can call it either a replication or a run one and the same. Okay, so we in general we need independent replications. Means I mean to say today when I run my simulation, okay, what the input I'm going to give to my model, got it, and what the initial condition I'm going to specify should be entirely different from tomorrow's. Okay, today the input and initial condition what I specified while running the simulation should be different from the input stream and initial condition that I prefer when I run tomorrow. Got it? This we call independent. Okay, so now to make you simpler, I took an example of banking system, but in your specified textbook, there's an example of a manufacturing system. Okay, yeah, the terms of the manufacturing system, yeah, the performance measurement, what I'm going to estimate in manufacturing system. Okay, the two performance measurements, what I'm going to estimate in manufacturing system resembles the two performance measurement parameters what I've discussed for banking system. I repeat, the two performance measurement parameters what I'm going to study in manufacturing system now resembles the two performance measurement parameters that we have discussed for banking system. Okay, and those two performance measurement parameters of manufacturing system are cycle time of parts and work in process. Okay, so what actually cycle time for parts is like response time of a customer. Got it? So cycle time for parts is the time from the release into the factory. I mean, what I said in case of response time of a customer, the time it arrives to the bank, to the moment it departs from the bank, right? So when is going to depart? After completion of a service. Clear? So similarly, cycle time for parts is the time from release into a factory until completion. Got it? So what is work in process? The other performance measurement parameter. It's similar to average queue length in a bank. Got it? So work in process means how we determine average queue length. So we need to determine the number of customers in the queue at all the points of time, that is T, right? Then we'll sum it and we'll divide, we will choose an integration because time is continuous. Got it? Similarly, work in process means the total number of parts in factory at any time. Work in process is total number of parts in the factory at any time. Got it? So now let me say, yeah, look at the slide. Okay, look at the second point. Okay, second point in for example. Okay, look at the second point in for example of simulation of manufacturing system. What I said, let Yij be the cycle time for jth part produced in ith replication. I need to tell you, I will make you understand what actually Yj. Listen, Yij is the cycle time for jth part produced in the ith replication. Okay, so here let me say, I say for example, I used to tell I'm going to run banking system for 100 times. Got it? Means 100 runs. In general, let it be R runs. Got it? So first column in table represents a run. Okay, 1, 2, up to R. That is totally R runs. Okay, and what actually in the look at the second column, first row. That is second column, first row. Y11, Y12, Y1, N1. Okay, so in case of first run, okay, let N1 be the sample size. In case of second run, N2 be the sample size. In case of rth run, NR be the sample size. Got it? I mean, sample size means, for example, in banking system, number of customers for whom I'm simulating. Got it? So now, in look at first row and second column, Y11 means, if I say it's a banking system, okay. Suppose if you're considering a banking system, Y11 represents the response time of customer number 1 in first replication. I repeat, Y11 represents the response time of first customer in first replication. Got it? So, but when I consider a manufacturing system, what actually Y1? Okay, let me not consider Y11. Let me consider Y21. So Y21, what actually it is? Response time of first customer in second replication or second run. In case of manufacturing system, Y21 represents cycle time for first part. Y21 represents cycle time for first part in second replication. Got it? So in general, rather than Y21, it is Yij. So what actually Yij now? Cycle time for jth part produced in ith replication. Now hope you got this point, right? So now, see here. This is the second column named but within replication data means within replication, within a run, within a particular run. Okay. What are the response time or what are the cycle times I've observed? For example, first row, second column, first row, second column. Got it? Those Y11, Y12, Y13 up to Y1N1 or the response time of individual customers or cycle time of individual parts observed within that replication, within that run. Clear? So now, like I said, I need to compute theta cap, right? Means I need to determine average response time of individual run. Got it? Or average cycle time of individual run. So here, look at the third column, that is across replication data. That, what is that Y1 bar or Y2 bar, YR bar? So Y1 bar is nothing but average cycle time. Okay, average cycle time for each part in one particular run. I mean, when I say banking system, Y1 bar is the average response time of each customer found in one particular run. Got it? So what is Y1 bar? Is the average response time of each customer found in one particular run. Got it? So like I used to use the theta cap, right? The same thing. With respect to manufacturing system, Y1 bar is the average cycle time of each parts in one particular, in first particular run. Similarly, Y2 bar is average cycle time for each part in second run. YR bar is average cycle time for each part in rth run. So E of theta cap, you remember, right? Estimation of theta cap is what? Theta. Got it? So like that. Now, if I now average of average cycle time or average of average response time, that is Y bar. Got it? So what actually S1 square, S2 square, SR square? They are nothing but variance. So I said you are clear with the basic concept. You need to have the basic knowledge of statistics, mean, variance, standard deviation. If just I have written S1, it's a standard deviation, but it's square, it's a variance. Variance and standard deviation, what it says? How far from the mean? This Y1 bar, Y2 bar, YR bar, what actually? They are the averages of each run, right? They are nothing but mean of each run. Got it? S1 square, S2 square, SR square, they are nothing but variance of each runs. And here H1, H2, HR, it's a confidence interval of which we have discussed in last session, right? Confidence interval. Clear with this? Got it? So hope you're clear with this. So now, let me say, now I need to now see here what I need output, and I'm dealing with what output analysis of terminating simulation. Okay, terminating simulation. Now I need to, I'm concerned with one performance measurement parameter, that is average cycle time. Clear? So what I'll do, I will perform some 100 runs, in general R runs. Got it? So after in each of the R runs, I will determine cycle time of all the parts. For example, say in second run, Y21, Y22, Y2N. They are the cycle parts of cycle time of individual parts in second run. Then with that, I'll compute Y2 bar. That is the average cycle time in second run. Got it? Then I have the average cycle time of each parts for all the runs. Then I will compute average of average cycle time, that we call mean. Got it? So how to compute average of average cycle time? How to compute average of average cycle times of all runs? I need to sum the, listen here, I repeat, to compute average of average cycle time of all the runs. To compute average cycle time of all the runs. We need to sum the average cycle time of all the runs divided by R. I mean sum y1 bar, y2 bar up to yr bar divided by R. Got it? So that is what, how to compute mean first. That is average. Y bar is nothing but summation of all average cycle time divided by R. So then variance, how to compute variance? You know, right? It's very simple. To compute variance, what? We have an average, we have a mean. We need to compute difference between mean and each element. You know, right? Difference between mean and each element, square that. Sum it, divide by R minus 1. Okay. So this is a basic concept, how to compute the variance. Got it? So S square, it's a variance. So confidence of once we have variance, we have a standard deviation. Clear? Square root of variance is nothing but standard deviation. Okay. So once we have a standard deviation, we can determine that error. Got it? What error may occur? So that is confidence interval of width. Error is computed as h equals t alpha by 2 r minus 1 s by square root of r. What is alpha? The alpha is determined through confidence level. Okay. Now within replication, continuous time data. Okay. For that we'll look at this slide. Okay. Within replication, continuous time data. See here. Across replication, we call it a discrete data because each replication is independent, right? Here, each replication, each runs are independent. So we call discrete. There's no connect. Today bank closes at 4:30 p.m. Tomorrow it commences at 9:30 a.m. So there's a time gap. There's a discrete. Across replications, discrete. But within replication, the moment bank commences to moment the bank closes in a day, time goes continuously. Okay. So what I said now, I am concerned with one more performance parameter, right? What is that? Average queue length in banking system. Here I am concerned with the average number of parts at any point of time. Got it? Average number of parts. Okay. So clear. What actually I said, work in process, average work, I need to determine average work in process. Work in process in general, total number of parts in factory at any time. Got it? So I need to determine average work in process. Yeah, now coming to within replication. Okay. So in previous slide, okay, I was telling that across replication is a discrete time data. Why across replication discrete means today I perform one run for a banking system from 9:30 a.m. to 4:30 p.m. Second run I'll perform tomorrow. Means there's a time gap. It's not continuous. So we call discrete. Across replications, across runs, it's a discrete. But within replication, I mean within a single run from morning 9:30 a.m. to 4:30 p.m. evening, time is continuously changing, right? Got it? So we call it's a continuous time data. Means data what we observe within a replication is continuous. Got it? For example, one more performance parameter, let it be average queue length in case of banking system, or average work in process in case of manufacturing system. Got it? So what I said, see here, within replication, okay, I said there's one function y of t, right? What is y of t? It gives number of customers in queue at time t in case of banking system. Okay. In case of manufacturing system, y of t gives number of parts. Okay. Y of t gives number of parts in a factory at time t. I repeat, y of t in banking system represents number of customers in the queue at time t. Y of t in case of manufacturing system represents number of parts in a factory at time t. Got it? So I need to determine average number of parts. Average number of parts in a factory in this run, on a particular run. Okay, means starting from time 0 to time t, what is the average number of parts that have been found in a factory, or average number of customers in a queue that have been found in a banking system. Got it? So within replication, this y1 of t, y2 of t, yr of t, they are continuous data because time is continuous. So now y1 of t represents number of parts at time t, y2 of t represents number of parts at time t. Okay, similarly yr of t represents at some other time t number of parts. So since t is continuous, to compute the average number of parts, what I need to make use? Integration. Remember, right? When time is continuous, to compute average, I need to make use of integration. So using integration, clear, right? So look, have a look at this. Within replication, continuous time data. So how average I'm going to compute? Using integration 0 to te yi of t dt divided by te in I. Here I means it's an ith run. Got it? It's an ith run. Clear? So similarly, I mean in the next run also I need to compute. See, for example, yi bar here means in ith run, what is an average queue length? What is an average number of parts in a factory? Got it? So to estimate this average queue length or average number of parts, average number of parts, okay, what we need to do? We need to determine average of average queue length or average of average number of parts in a factory. Got it? Clear? So that we'll denote as y bar. So for an ith run, average queue length is given as you can see in the slide. Got it? Okay. Now, what about also for an ith run, average number of parts in a factory is represented by the same average expression, same mean. Okay, that is yi bar equals 1 by ti integration of 0 to ti yi of t dt. And sample variation, you know how to compute sample variation, right? The same, but here we have applied for a function y of t. Got it? So what actual sample variance? We need to compute difference between mean and each element. Mean and each element, we need to determine difference. We need to square this difference. We need to sum all, and we need to divide by time. That is an average. Got it? So since it's a continuous time data, a confidence interval of what is given as z alpha by 2 si by square root of ti. Okay. Now this is just a review of math output analysis for terminating simulation. The main thing to highlight, I said, across replication data are independent and identically distributed. So across replication means across different runs. Today I'm going to run a banking system. Okay, tomorrow also I'll run a model for a banking system. Today's instance input stream and initial condition might be entirely different from tomorrow's initial condition and input parameters. So we call across replication data independent and identically distributed. Okay, within replication data are not independent and not identically distributed. Mean when I run the simulation within replication means within the same run. Got it? So initially I will specify some initial condition and I will generate some random input through a random number generator. And for that random number generator, what the seed we are going to give. So based on the seed, the same means we can determine the subsequent random inputs that will be generated. Okay, so random number generator generates random stream based on the seed value. Clear? Got it? So within replication, data are not independent, but across replication, data independent. Okay, clear? So now coming to output analysis for steady state simulations. Steady state simulation means non-terminating simulations. And one more, when I say non-terminating means it doesn't mean that it never terminates. Of course it will terminate, but after an infinitely larger time. I mean to say, let me say you have a cable network, right? You have cable connection in your home. Okay, for your television you have taken a cable network, a cable connection. So sometimes you can able to watch movies, you can be able to watch all channels. Okay, but what happens in some uncircumstances? Got it? If any problem occurs, then you won't receive cable signal. Got it? So I mean to say cable connection is an example for steady state simulation. Got it? Clear? So now here the main thing is that same, let me consider our single run. Okay, single run, and single run means see here we may start a simulation at time 0. Got it? So even in terminating simulation, I'm starting the simulation at time 0. Clear? So here in non-terminating simulation, I won't consider start time to be 0. What I'll do, I will start a simulation at time 0. Then I will allow the simulation to run until some time t0. Okay, I'll tell you. Initially, I'll start the simulation. See here in non-terminating or steady-state simulation. Okay. Of course, we will start simulation sometime 0 with some initial conditions and some input streams. Okay, but we'll make it to run for some time. Okay, until my clock fixed to t0. Some clock fixed to t0. Okay, when clock stick to t0 means we feel that system has reached a steady state, some stable state. Okay, then from that particular point of time t0 towards the end time t, we are observing the performance parameters we require. Clear? So let y1, y2, and yn be those performance parameters. Okay, those output measurements we got from non-terminating simulation from time t0 to t. Got it? So suppose I'm simulating a discrete, suppose I am concerned with a discrete measurement. For example, like average response time. Okay, I mean to say, see here, assume a bank. In banking system, it is going to wind up. Okay, I can't take banking to be a better banking system. Can't be taken for as a better example for steady state simulation. Okay, assume like cable network or some factory, manufacturing factory, which runs continuously for a month. Okay, for a month. Got it? So in that case, okay, I'm similar to manufacturing system. Okay, there are some parts, right? So for entire month, some parts being generated by a company, manufacturing company. Got it? So what may be the average cycle time for producing each parts? What may be the average cycle time for producing each part? So how to compute? We need to know the cycle time for all the parts, sum it, divide by n. But here I said it's a steady state simulation, right? Means I'm running the simulation for infinitely larger time. Means in this I'm observing cycle time for almost infinite number of parts. So here we use n tends to infinity. Okay, so clear with this? In non-terminating simulations, we are observing the cycle time of infinitely larger number of parts, because the simulation is being run for infinitely larger time. So we need to sum, got it? Cycle time of all the parts, okay, then divide by n. And in this case, n is infinite, it approaches to infinity. Similarly, suppose we need to determine average work in process. Got it? What I said, y of t represents work in process. Got it? At time t. Got it? So from t naught to t, that is infinitely larger duration, let me have this y of t. Got it? For each times. Then we know, since time is continuous, to determine average work in process, you should make use of integration 0 to t. Okay, y of t dt, and we need to divide by t. And the t, as I said, it's a steady state simulation. T approaches to infinity. Got it? Now, see here, there will be bias. See here, there will be a bias. See, I have produced my, I have developed a model. I given to my client, okay, stating that the point estimator is some x. Later, he will find the point estimated, he will determine performance to be x.0003. Means there's a bias in what I stated and what he has observed while experimenting, right? So that bias is nothing but difference. So this bias usually occurs because of sample size. Okay, the way we choose sample size. Got it? So we need to choose a sample size such that, okay, it will reduce a bias. It will minimize the bias that may occur. So so sample size should be selected such that any bias in the point estimator should be avoided or should be reduced. Okay, bias can't be avoided but should be reduced, minimized. Okay, and the sample size should be such that there should be a precision in the point estimator, means accurate. Okay, and the sample size should also be selected considering budget constraints. Got it? So coming to notations, as usual, theta for discrete measurement, discrete performance measurements, pi cap for continuous performance measurement. Got it? So to reduce the bias, now in this slide we will have a look at two methods through which we can reduce the bias. Got it? So bias can be reduced, okay, using two methods. One is what we call an intelligent initialization, and the other one is we can divide simulation into an initialization phase and a collection phase. Actually, I told you about the second point, but I'll tell you what actually it is. Got it? So in this slide, what we are going to see, how to reduce a bias. I repeat, in this slide, we are going to discuss how to minimize the bias. So bias usually occurs because of sample size. Got it? I told you. Clear? So to reduce bias, there are two methods. One is intelligent initialization. The other one is divide simulation into two parts. Divide each run into two things, two parts: initialization phase and data collection phase. Okay. Intelligent initialization. Initialize the simulation in a state that is more representative of long-run conditions. And next, if the system already exists, okay, if the system already exists, we can collect data from that system, right? And we can make use of that data to specify accurately initial conditions. Clear? Next, if the system can be simplified enough, okay, say for example, queuing models, okay, we can solve the simplified model to find long-run expected or most likely conditions. Clear? So this is about intelligent initialization. Means the the way we select initial conditions. Clear? So next, the second method, what I said, to avoid bias, we need to divide simulation into two phases. One is initialization phase and data collection phase. Okay. So what actually initialization phase means, I'll tell you. So till now, what I said, when discussing terminating simulation, starting time is always 0, right? But a few 2 or 3 minutes before, when I start explaining you a steady state simulation, what I told, let me start the simulation at time 0, okay, and let me not collect data until the clock fixed to t0. Got it? And from t0 to t, let me observe the performance. Clear? So initialization phase means here, of course, we need to run. The starting time is always 0, but from the time 0, immediately we are not going to observe the output measures. We'll wait until the clock fixed to t0. Starting from t0, we will observe, we will gather the data. Got it? So this is called an initialization phase. Okay. So once we reached an initialization phase, clock fixed to t0, then from that time to an end time, we can gather the data, collect the data. Clear? So this is about the second method of minimizing the bias. Got it? I mean, from time 0 to t0, there may be some observations, but those observations I'm not considering to compute point estimator. Clear? So I'm considering only those observations after time t0 to te, and those observations I'm going to consider for computing point estimator. So the bias in the point estimator will be minimized. Clear? So this is about an important topic, output analysis for terminating and non-terminating simulations. Okay. Thank you for listening.